Welcome to the session. Today we are going to discuss Module 1, Mathematical Logic and Predicates. In that question bank we are going to discuss. In the question bank, short answers we are going to discuss. Let us go for the first short answer. What is a statement? Define a statement and atomic statement. So, statement is nothing but any declarative sentence. Any declarative sentence which is having either true or false. Then such declarative sentences we are calling it as a statements. Suppose if I am saying that Bangalore is the capital of India. So that is, we can say that that is having truth values. So either it may be true or false. So suppose if you are going to consider the example, let us say Bangalore is the capital of India. So here it is having truth value. It's a declarative sentence. The truth values are either it is true or false. So such declarative sentences we are going to call it as a statement. Suppose we are going to consider a sentence like this. Let us say, how beautiful. How beautiful. So how beautiful. It's not a declarative sentence. It's not a declarative sentence. So we are not going to consider this is a statement. So a statement is nothing but any declarative sentence which is having either true or false. Such declarative sentence we are calling it as a statement. Next, another definition. What is atomic statement? In mathematical logic, a statement which cannot be broken into smaller statements, then such a statement we are calling it as a atomic statement. So it is not going to divide further. Suppose if I am going to take Bangalore is the capital of India and the Hyderabad is capital of Telangana. So whenever if you are going to consider this is one sentence and this is another sentence. So they are throughout we are going to call it as this is also a sentence, but it is made up of two sentences, and these two sentences it is not going to divide further. So we can say that these are the atomic sentences. So atomic sentence in mathematical logic is a statement which cannot be broken down into smaller statements. So such statements we are going to call it as atomic statements. And now the another definition. Explain logical equivalence with an example. See here, logical equivalence. When we say that two statements are logically equivalent. See here, one statement, let us say, I am just saying that P to Q. This is a conditional statement. So this is equivalent to another statement. Whenever from this we are going to derive the other statement. So here let us say negation of Q or negation of P or Q. So this we are going to call it as both are equivalent to each other. That means logically equivalent means we are going to derive from one statement to another statement by using logical rules of logic. Then if you are going to get the other one, then we can say that both are logically equivalent, and this is going to be denoted with a symbol like this. Or else we can say that both are having same truth values. So here it is identical truth values. Suppose if I am going to consider, let us say P and Q. So here two proportions are there. So there are, I am going to consider two ones. There is a 2 to the power of 2 possibilities will be there. So 2 to the power of 2 is nothing but 4 possibilities will be there. Let us consider true, and the next false. Then again I am taking it as true, false and true, false. Then conditional statement. So I am going to consider if P then Q. So what is this? This is true, this is false, and this is true, and this is also true. And let us consider negation P. So negation P, if I am taking this is false, then this is true, and this is true. Now negation P R Q. Negation P R Q. So this will be true, this will be false. Just observe this. These two are going to concentrate. Then this is false, and this is true, and this is true. Now observe, these two are equivalent. These two are equivalent. All the truth values, true, false, true, true, false, true, true. So all the truth values are identical. Then we can say that both are logically equivalent to each other. Logically equivalent to each other. Or we consider the another example. If Lisa is in Denmark, then she is in Europe. And if Lisa is not Europe, then she is not in Denmark. So like this also we can say that the whenever the compound prepositions are, one compound prepositions we are going to take by applying rules of logic, and if you are going to derive the another one, then we say that a derived one and the given statement both are logically equivalent, or else we are going to construct a truth table. Then all the possible combination of truth values both are identical, then also we can say that they are logically equivalent. Now the another one is, what is a tautology? So tautology is nothing but is a logical statement in which the conclusion is equivalent to the premise. It is the formula in proportional calculus, which is always true. That means for all truth values, then if we are going to get the compound proportion or logical statement, if it is true, then we can say that is a tautology. Otherwise, it is not a tautology. So if all are false, then we can say that logical statement is a contradiction. So if some are positive, some are negatives, then we can say that it is a contingency. See, any logical statement, if it is having for all truth values it is true, then we can say that is nothing but a tautology. Then if for all the truth values, then the logical statement is false, then it is known as a contradiction. Then it is mixed, both the truths and false, then we can say that it is contingency. The logical statement is a contingency. So these are the possibilities will be there for any logical statement if you are going to consider. Then the another one is, so here write a converse, inverse and contrapositives of the following prepositions. So here, if P then Q to R. If P then Q to R is the given conditional statement, and then the converse if you are going to write it as converse. So which is nothing but, then we are going to take it as Q to R then P. It is a converse of this. So if I am taking any conditional statement P to Q, the converse is nothing but Q to P. Converse is nothing but Q to P. This is converse. And next, suppose if I am going to take another one is contrapositive if I am going to take. So contrapositive. So contrapositive is nothing but a negation of negation Q to negation P. Negation P. If I am going to consider inverse if I am taking, then negation P to negation Q. These are the ways, that means whenever any conditional statement is given. So for that, what is a converse and what is a contrapositive and what is the inverse? So based on that, we are going to write for this, the converse is by using this, we can write the converse, and next the contrapositive, we are going to take it as the given implication and the contrapositives both are equivalent. So negation of, in the place of Q, we have Q to R then negation P, then negation P. So this is known as a contrapositive for the given proportion. And next, suppose if I am going to find out what is inverse. What is inverse? So it is nothing but negation of P, then negation of Q to R. So this we are going to say that this is the inverse of the given proportion. Or else we can simplify this. And we can write in another form. So let us say negation P and negation of negation Q to R is equivalent. Then again we are going to write it as double negation, send negation inside Q and negation R. So negation P, then Q and negation R. Like this also we can write the inverse of the given proportion. Now, what is NAND and NOR? So here NAND is nothing but a logical NAND, or not and. If you are going to apply is an operation. If you are going to apply both on the compound proportion, then we are going to get the NAND operation. See here, NAND is an operation on two logical values. Typically, the values of two proportions that the produces a value of true if and only if both of its operands are true. In other words, it produces a value true if and only if at least one of the operand is false. Suppose if I am going to say, we are going to denote P and Q are two proportions. So then I am going to write negation NAND. Let us say NAND we are going to define like this, and NOR we are going to define like this. So NAND is nothing but, NAND P, NAND Q is nothing but equivalently negation of P and Q. NOR is we are going to denote with the symbol, and which is equivalently written as negation of PRQ. So from this, suppose I am going to take it as a true, false are the truth values of P, and true, false are the truth values of Q. Then we are going to consider first one is P and Q. P and Q is nothing but just we are going to write it as, let us say P and Q is, for P and Q both are true, then this will become negation of that. So it is false. So it is false. So for that the negation is true. And this is again P and Q, then this is nothing but false, and the negation of false is true. And false is also false, negation of this is true. So that means just we are going to find out what is P and Q for these two combinations, P and Q. So P and Q, what I am going to get? If P is true, Q is true, Q is true, then I am going to get, let us say, P and Q. So what is the P and Q? It is true, then it is false, then it is false, and then it is false. So the negation of this is a NAND. So it is a false and the remaining are true. And NOR is a negation of PRQ. What is a PRQ here? PRQ, if I am going to consider, this is true, and this is true, and this is true, and this is false. So negation of this, we are going to get false, then it will be true. So this is the way that we are going to calculate the NAND NOR. So like this we can produce order the NAND operation and as well as NOR operations. Now let us go for the another one. Demonstrate the conditional and biconditional statements. So whenever if I am going to consider a conditional and biconditional statement, already we just saw that if P and Q are two statements, if P then Q, then it is nothing but a compound statement. Why we are calling it as a compound statement? It is made up of two statements, P and Q. So it is a compound. Then it is going to be denoted as P if P then Q, and it is referred as a conditional statement or implication. or implication. So this is just we are going to consider once again by using the truth table PQ, then P to Q, it is true, true, then false, false. Let us take the four possibilities are, then it is a true, false, then it is a true, false. Then if both are true, then automatically it is true, and one is true and one is false, then it will be false. And next false, true, then it will be true. False, false, it is true. False, false is true. So this is the truth table regarding the implication or conditional statement. Conditional statement. And another one is a biconditional statement. So biconditional statement is denoted with this P biconditional Q, and which is equivalent to if P then Q and if Q then P. If P then Q. If P then Q. If P then Q and if Q then P. If Q then P. So suppose if I am taking if Q then P, I am going to calculate from this. So it will be true, then it will be true, then it will be false, then it will be true. So true, true is true, false, true is true, and true, false is false, and false, false is. Now I am going to find out what is a biconditional. Biconditional we are going to denote it with this, and which is logically equivalent to if P then Q and operation. If you are going to perform on these two, then it is true, then it is also false, then it is false, then it is true. It is true. So this is the biconditional statement of P and Q. Of P and Q. So the definition shows what is the conditional and what are the biconditional, and what are the truth tables of this. Now define a contradiction. It's already we discussed. One is for all possible combinations. See, contradiction is just for all possible combinations of the truth values of the given proportions. If it is false, then we can say that it is a contradiction. It is a contradiction. So for that, so here only I am just taking one proportion. So that is nothing but a P we are taking. It is having truth values are true and false, and a negation false and true. Then P and negation P. P and negation P. We are going to get this. So we can say that P and negation P is a contradiction. Is a contradiction. And of course, we are going to discuss already this. So what is the inverse, converse, and contrapositives? So it is if P to Q will be there, then the converse is Q to P. That is if Q then P. We are calling this as if Q then P. If Q then P. And contrapositive of P and if P then Q is negation Q, if negation Q, or if Q negation Q then negation P, or if not Q then not P, not P. And inverse of this conditional statement is nothing but negation P then negation Q, or if not P then not Q, then not Q. Here the given conditional statement and its contrapositive. Its contrapositives. Both are logically equivalent. Both are logically equivalent. Whereas the inverse and converse also both are equivalent. Now let us go for the other short answer. Translate the following statements in symbolic form. So here what is given? All men are good and no men are good. No men are good. Okay. So here it's not there. Let us say no men is good. Okay. Right. So here we are going to write no men is. Now to translate this into a symbolic form, we are going to use a predicate calculus concept. So let us say the predicate or open statement. So P of X is equals to, so X is a man. X is a man. Then we are going to take another predicate. Let us say Q of X. So X is good. X is good. X is good. Now A we are going to write for all men. That means for every x, see here x is a man and x is good. So we are taking for every x. That means for all men. Okay. So for all men. So if he is a man, then he is good. If he is a man, then he is good. So the symbolic form of the given statement as all men are good, then this is the symbolic form. And B, no man is good. See here, we are saying that the equivalent form of this, for all x, if x is a man, then the equivalent form we are taking, then x is not good. The equivalent form of the above we are going to consider like this. Then symbolically we can write it as for every x. For every x, if p of x, then negation of q of x. So this is for b. So translate whatever the statement will be there. Then we are going to construct a symbolic form by using a predicate calculus. Then the next one is the another example. So we are going to consider explain the square of an odd integer is an odd integer, and the direct proof of the statement, the square of an odd integer is an odd integer, and indirect proof of the statement, n square is an odd, then n is an odd. Okay, while we are going to consider these things, and now let us go for we are going to discuss the first one. So if n is odd, then if square of an odd integer is odd, the square of an odd integer is an odd number. So for that we are going to consider. So let us go for this the direct proof of the statement. So the square of an odd integer, So let us go for the odd integers are. We are going to take it as taking the contrapositive for this, the equivalent form we are going to consider. Then the equivalent form we are going to take it as. So for this, if n is not odd, then n square is not odd. So I am taking the integer as n. So then what is given? N square. If I am taking an integer is n square is odd. Then is if a square of an odd integer is an odd square of an odd integer. So here, if n is an odd, then n square is an odd, then n is odd. Then we are going to say that then is odd. So then the contrapositive for this is, if n is not odd, then n square is not odd. So we are going to take the contrapositive as like this. So we are going to prove this. So n is not odd means n is even. So we are going to say that. So both are same. We are going to say that n is equals to 2k. So here I'm just taking, then n square is equals to 2k whole square. So it is nothing but 2 into 2k 4k square. That can be written as 2 into 2k square. 2 into 2k square. So we are going to multiply with 2. So it is obviously it is even. Obviously it is even. Hence we can say that n square is, from this we can say that n square is odd number, is not an odd number. That means n square is even. N square is even. Then we can say that what is that? N is for this we are going to say that n is even. N is even. Then n square is even. Then the n square is even. So the contrapositive we are going to take it as like this. So n is not odd, means it is even. Then n square is not odd, means n square is even. N square is even. Or this is one way we are going to take it as, this is nothing but the indirect, this is if n is odd, that is n is not odd. N is not odd, or directly we are taking, and we are going to prove this. This is a indirect proof of this. So next another one is the direct proof, the square of odd number. See, this is the second one. This is second one we are taking, and the first one is the direct proof. N is odd number, odd integer. So let us say odd integer means we are going to write n is equals to 2k plus 1. 2k plus 1. See, for every k, whatever the value of k, then this is even plus 1 is odd. So we are taking n is equals to 2k plus 1. Then what about n square is equals to 2k plus 1 whole square. This is 4k square plus 4k plus 1. So this we are going to write it as 2 into 2k square plus 2k plus 1. So from here up to here it is even plus 1. So we are going to say it is odd. So that we are going to say that if n is, the square is odd number, then we are going to say that n square is odd number. Then we are going to the square of odd integer. That is, I am just taking n is odd. We are going to write this is the square of odd integer is an odd. So that is, if n is odd, then n square is odd. N square is odd. So like this. If n is odd, if I am taking p is nothing but n is odd, let us take, and q is n square is odd, then we can write it as n square is odd. Then we are going to consider it as this as a p to q. This as a p to q. Okay. So this is the, in this way we are going to prove the direct one. That is a square of an odd integer is an odd number. So that means if n is a odd integer, then n square is also odd, we are going to say that. Or equivalently we can say that if n is not odd, then n square is not odd. It is nothing but indirect proof. That is, we can say already we are discussed about the given conditional and its contrapositive is equivalent. So suppose if I am taking p, if I am taking is a n, if I am considering in this form, then I am going to get p to q. That is, if n is odd, then n square is q. Then what is the contrapositive for this? Negation of q to negation of p. That is, if n square is not odd, then n is, if n square is not odd, then automatically we can say that n is odd. So n square is not odd, then we are going to say it is. So this is the way that we are going to prove the direct and indirect proof of this. And now another one is, if you are going to consider the biconditional, this is show the value of a p biconditional q in terms of this. So we are going to take it as p biconditional q, which is equivalent to if p then q and if q then p. Then this is a negation P or Q and negation Q or P. Negation P, Q or P. Then this we are going to write it as. So is itself we can say that in terms of this, or else if you want to simplify that, negation P or Q and negation Q and R, then we are going to write it as negation P or Q and we are going to take it as a P and we are going to take it as a P. See, this is we are going to take it as this is equivalent form is negation P or Q and negation Q or P. Either we can keep here or else if you are going to further simplify, then we are going to get like this. So negation P or Q and P. So we are going to get like this. So this is going to be like this. Next, this we are going to write negation P and negation Q or Q and negation Q and this Q and negation Q. Then what about this R? Just I am going to further simplifying this P, then R, next Q and P. So this is we are going to say negation P equivalent negation P and negation Q, and of course this is nothing but a contradiction. Contradiction are the given premise is itself only. Then here this is a contradiction. Contradiction are whatever the value of Q or P, then we are going to get P or Q. So this is the we are going to represent a biconditional P biconditional Q, which is the equivalent form is consisting negation or and. So like this we are going to see another one is so with this show that the value of P biconditional Q in terms of only negation or and terms only. Then with this we are going to conclude these short answers which are related to mathematical logic which is there in the first module, and next session we are going to discuss the short answers and the descriptive answers for the module 2. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.